Okay, ladies and gentlemen, in today's video, I want to introduce some of the concepts of one of the next things that we're going to be doing, which is talking about electromagnetic waves, and from electromagnetic waves, jumping into the idea of optics and geometric optics. So today is going to be a lot of jargon, a lot of definitions, and a lot of properties of what it means to be, well, I guess first a wave, and then an electromagnetic wave. And then once we have established the idea of electromagnetic waves, what are two of the most simplest phenomena that we can talk about that these waves do? So that's what the goal of today's video is going to be. So again, make sure that you're ready to take it all in, a little bit slow, a lot of jargon, okay? Make sure that we're processing each and every one of these words. A lot of this we're actually already familiar with from previous topics that we've studied together, but I want to make sure that just for the record, we get to cover all of it. That way, just in case something is a loose end for some of you, depending on who you took Physics 1 with versus Physics 2, that we're all on the same page. So let's jump right in. Okay, so like I said, a lot of jargon, right? Here we go. So what do I mean by the idea of electromagnetic waves, and optics? Well, the first thing that we should really make sure that we all agree on is what is the actual definition of a wave itself? Or better yet, what are the properties of waves that distinguish it from the ordinary things that we talk about in this class, such as particles, okay? So the first thing that I really want to make sure that we're all on the same page with is what are these properties? So a wave, okay, is something whose motion is oscillatory. Oscillatory is a word that we use simply to mean the word repeat, right? So, you know, when you have a water wave, right? The pattern repeats, right? When you do this thing with your arms, right? The pattern repeats, right? When something goes in orbit around a planet or something, right? The motion repeats. That word repeats is oscillatory, okay? But it's not enough to just be or have a repeating motion. Obviously, we're going to see some of that is going to be implied. We have to have a laundry list of properties that turn out to be something that we can typically measure about a wave, okay? These are in no particular order. These are just ones that, you know, it's the way that, that they just came out of my brain when writing this last night, okay? So if waves have an oscillatory nature, then the first thing that they have to have is a period, right? We've seen this when we talked about planets going around stars, or moons going around planets, right? That when you have a repetition motion, right, you can define the time it takes to complete one repetition. And we call that the period, okay? Here, if we're talking about a wave, right, that oscillates up and down or something, then it's the time required to complete one oscillation of that wave. If it's a time, like always with period, it's measured in seconds. And typically, even though, yes, it's just a time, we typically denote period by being that capital T with the little hats, as opposed to just being any old time T, just to signify that it's a time that carries some extra information, right? It's time that refers to an oscillatory motion, okay? We also know from doing this, same thing with planetary motion, right, that period is related to two types of frequency: regular frequency as well as angular frequency, right? Angular frequency was that if the thing is implied to go around in a circle. Obviously, that was the important one for planetary motion. But we also know that it's related to regular frequency, right? And what again is the definition of frequency? It's the amount of cycles that you complete in a second. Anyway, it's the inverse of period. If period is the time required to repeat a cycle, frequency then, how often it occurs, is the amount of cycles that's completed in a given time frame. Here, typically we use a second, right? Frequency has units of 1/seconds, if it's the amount of cycles, the stuff per second, okay? And another word for that is hertz, right? 1/seconds is also known as a hertz. And the big way to link that property 1 and 2, period and frequency, is that they are just inverses of one another. So if we know something's period, we simultaneously know its frequency, and or vice versa, okay? Scrolling down a bit, okay, we have some more. The wavelength of an object, okay, or of a wave, right? That says how long is the wave, right? So if you have a wave that just keeps on going, because a lot of waves tend to be infinite, that doesn't necessarily mean that its wavelength is infinite. It means one wavelength is defined as the length of the wave up to where it is a unique piece, and then it's just a carbon copy or a repeat of one another, right? So that length that it takes to form one complete wave is what we call the wavelength. We give that the Greek letter lambda, okay? That's this little scripty looking thing down here, okay? And obviously, if it's a length, its units have to then come in our standard of length, which is meters, okay? And amplitude, how high, the max height of a wave, right? We know that waves, they come in peaks and they come in troughs. The amplitude, no matter which side of that scale you're looking at, is going to be the same. So we're saying the max overall distance from node or distance from zero, right, of the wave is the amplitude. The unit that comes with that varies. It depends on the type of wave, right? A water wave will have an amplitude of some height, right? Whereas a sound wave would have some amplitude that is in decibels, right? A measure of sound, okay? So the amplitude carries the information of the unit of the wave, right? And so different types of waves, the units of amplitude would all be different. And hopefully that should make sense. Okay, but nonetheless, it's one of the properties that we have in waves. Angular frequency. Again, this is taking us a step back to point number 1 and point number 2, is that we said that period, we know, is the time required to repeat one cycle. Frequency is the amount of cycles completed in that second. But what if the period or the motion happens to be going round or is implied in some sort of circular motion or trigonometric motion, right? Then we know there is a relationship between the regular period, the regular frequency f, and the angular speed or angular frequency, which is just 2 pi times f. That's this formula right here. But we also know then that there is a relationship between angular speed and period, which is omega is equal to 2 pi over period. And this is the one that we actually used quite often back when we talked about gravity and planetary motion, right? This is the one that we used way back when, if you remember, to plug into Newton's laws when solving for his version of Kepler's second law, okay? And so that equation should be familiar to you, okay? This one's next, number 6 is a little bit of a weird one. This is one that we typically don't use in our everyday language, and we also haven't seen any sort of analog of this come up in this class yet, and that's the idea of wave number, right? It's a symbol K. It has a formula, which is 2 pi divided by the wavelength. So it's related to the wavelength in a very similar fashion to the way that angular frequency is related to frequency. Namely, you're scaling it in some ways by 2 pi. Here, though, instead of just multiplying 2 pi, we're taking 2 pi and dividing it by the wavelength, right? Which means that it has a weird unit, 1 over meters, inverse meters, okay? And what wave number really corresponds to is it points to the numbered trough or peak that you're talking about in a given wave, right? Because if waves have, this goes on forever and one segment of it is a given wavelength, well, then we can count out how many of those peaks and crests we get to a certain place. That's what we're measuring with this wave number K, 2 pi over wavelength, okay? Again, it's not of tremendous importance as to what that actually does for us, but we're going to see why it's of symbolic importance in a little while. But let's first keep going down with the rest of our list of properties that waves have, because we're not done yet. There's a lot of properties these things have, right? They have a speed. They have some wave velocity, right? You can have a wave that's moving across, right? You throw a rock onto the water and then boop, you watch the water wave go out, right? You're at a stadium and people start doing the wave, right? You have a speed as to which that wave moves across, right? Sound wave, the sound leaves my throat and I guess comes to this microphone over here, right? But it does so at some speed. An electromagnetic or light wave leaves that light bulb and gets down to our eyes at some speed. As it turns out, okay, for any wave, the velocity of that wave is equal to its frequency times its wavelength, which is so cool because if you have a wavelength, one of the properties, and you have a frequency, one of the properties, that means you're implied then to have a velocity if velocity is just wavelength times frequency. So we kind of get that for free, that if we already know the wavelength and frequency, we now also then know the velocity. Another way of saying that too, right? Because wavelength is related to wave number, and angular velocity or angular frequency is related to frequency. If we know one of those, we know the other, and therefore know the velocity as well. Okay, so that's very, very important for us to see. Okay, what else do waves do? They spread, right? They disperse, right? Waves, maybe they go on forever, but that doesn't really happen in the physical world, okay? So they have some sort of spread. They have some sort of dispersion pattern, right? You know, the best example I can think of, right, is you yell out, blah, right? And as that sound travels, it disperses, right? Okay, it loses some of its amplitude modulation, and therefore eventually the sound just peters out, right? Same thing with ripples when you throw a rock into the water, right? It hits in the middle and then it goes out, but eventually it disperses and goes away. People at a baseball stadium, they start the wave, they think it's a good idea for like what, I don't know, 3 minutes, and then it goes away, right? Because people get tired of it, right? Waves spread, they disperse. Another way of thinking of this too, instead of just that sort of dispersion, is spreading, right? Light leaves a light source, and let's say that we have like a little crack in a door, right? We know that when the light comes through the crack in the door, it doesn't just go in a straight line, right? It spreads out light a lot greater than the width as to which it comes in. Light spreads, or waves spread, okay? This is one that we typically don't think of, but all waves need a medium, right? They need something to exist in, right? And here we are back to this thing that keeps coming back up over and over again in this course, right? That there is really a whole lot of philosophy to physics, right? That in order for a wave to exist, it must exist in something, right? The medium is what that wave exists in, or what it travels in, however you want to phrase that, right? So a water wave, the medium of water wave is the water itself. Without the water, there could be no water wave. Air, or air molecules, are the medium for sound waves to travel. Without air, there's no sound, which is why you always hear about, no pun intended, but they always get wrong in movies, right? That there's no sound in space because there's no air in space. Space is a pure vacuum, and so there is no medium for sound to travel, okay? People doing the wave at a baseball stadium. What's the medium for that? It's the people, right? The people are the medium itself. And historically speaking, trying to figure out the medium of some waves has led science to some absolutely amazing conclusions. Believe it or not, we know all the physics that we know and love today because of Albert Einstein. And really, when Einstein set out on his quest to reinvent all of physics, chemistry, and biology and mathematics, he started this quest by trying to provide an answer to a very simple question, which is, what is the medium of a light wave? Okay, and it turns out that that question has a lot of tentacles, that in order to push those tentacles back and actually get down to the solution, you have to really rethink the way that you see the world. And so it was really that question, talking about this medium, this property that exists of an electromagnetic wave and what it really is. And there was a big debate about this in the 1800s, and it really got us to where we are today. Okay. Last but not least, right, we know that waves interfere, and there's two words that come with interference, both constructive interference and destructive interference, right? If you've ever sang in a choir or listened to a choir sing, or a cappella, right, you know that different sounds, people singing different notes, interfere with one another and sometimes produce absolutely amazing, beautiful tones, right? You take single notes and you form chords, right? This is all constructive interference. Or someone singing the same note and someone next to you singing the exact same note, you put the two together and they become louder, right? This is amplitude constructive interference. But if you've ever sang in a beginner's choir, you probably have also heard destructive interference, right? When someone next to you is singing a note that's half a step off or something, you know, and the two combine to be a much less pleasing tone, destructive interference, right? Waves can interfere constructively, help the waveform or the amplitude out, or they can interfere destructively. These are not them, but very famous invention from, I don't know, about 15 years ago, which a lot of people now have, is noise canceling headphones, right? What does a noise canceling headphone do? They have a small microphone in them. They take the surrounding noise around you. They take it into that microphone. They put it through a small processor in the headphones, which takes that waveform and finds the inverse waveform, namely the complete opposite as best it can, the complete opposite waveform, and then plays that backwards waveform in your ear as close to a match of the volume as it's coming into your ear, thus canceling the noise out almost completely. Destructive interference. Although that's destructive interference used in a very positive way. Okay, those are our 10 properties of waves. And so with those 10 properties of waves, I want to make sure that we are all in agreement that if in particular we're going to be focusing on a very special type of wave, namely electromagnetic waves, then we know that we get a freebie that if we're talking about an electromagnetic wave, we always know its velocity in vacuum, and that's the speed of light, 3 times 10 to the 8th meters per second. And that's such a special velocity that we give it its own special symbol, lowercase c, 3 times 10 to the 8th meters per second. So if you're given a problem, okay, and I tell you that it is an electromagnetic wave, we automatically get an implied freebie that the velocity is 3 times 10 to the 8th meters per second, or c. Cool. Now, what is the general mathematical form for a wave? And I think you might have seen this in lab already, but let's talk about it some more, okay? A wave has 2 variables, space and time, position and time, okay? So we say that the equation A, which of those 2 variables, x and t, is a wave if it has the following form. Some number times some trig function, and inside that trig function, you have some number times the x variable plus some number times the time variable, okay? Now, that's what it means to be the form of a wave, so the trig function can either be a sine or a cosine. Let's find out then what each of those numbers has to be based on the definitions that we just laid out. Well, we know that when we put a sine or a cosine into our calculator, right, we always put the sign of a number, right, the sign of 25. We never put the sign of 25 meters or the sign of 25 seconds, right? Trig functions bear no units. So that gives us a hint that we can use dimensional analysis to figure out what numbers have to be in front of the x variable and what numbers have to be in front of the time variable. Well, again, if something is in front of a position variable and it multiplies that position variable, and the result has to have no units, the position variable has units of meters, so whatever is in front of it has to have units of inverse meters or 1/, meters. We've already talked about a wave property that has units of inverse meters, and that was number 6, the wave number. So it's the wave number that gets multiplied in front of the x position. By the same token, dimensional analysis tells us that there's got to be something in front of the time variable, right? Because again, we don't put 5 seconds into our calculator, and whatever's in front of that time variable has to have units of 1/, seconds. Now we have 2 candidates for that, frequency or angular frequency. But remember, these are trig functions, right? And trig functions are always scaled to the unit circle, which is 2 pi, which is why that thing in front of the time variable is not the frequency f, but the angular frequency, because we're talking about trig functions. Last but not least, the number in front of that trig function, right, tells us how high or how low that trig function will scale. This has no choice but to be the amplitude, which is also why it will carry the units, because it's the only thing in here that comes out to have units not be canceled. Okay, so having now said that, the general form for a wave then, A as a function of position and time, is the amplitude times a trig function times the wave number k times the position variable minus the angular frequency times the time. Cool. What's an example? Down here in blue, I say, suppose that I have a wave A, and its formula is 5 cosine 3x minus 4t. From that, Tell me everything you possibly can tell me about the wave. Well, let's go. Right away, by just knowing that the general formula for the wave, right, is this thing, a x of t is a0 sine kx minus omega t, or cosine, because we get to, doesn't matter, right? What's the amplitude of that wave in blue? 5. What is the wave number k of that thing in blue? 3. What is the angular frequency of that thing in blue? 4. Why? Because it's the thing that shows you kx minus omega t. We're just peeling off the k as 3, peeling off the omega as 4, peeling off the amplitude as 5. But then it doesn't stop there. Because we know if we know k and we know omega, we can find their other corollary quantities, such as k was equal to 2 pi over lambda. So if we have k, we can find lambda. It's just 2 pi over k. If we have angular frequency, we know that angular frequency is 2 pi times the frequency. So therefore, we can find the frequency by just taking our angular frequency and dividing it by 2 pi. But now, if we know the wavelength, lambda, and frequency, f, we know the velocity of that wave is frequency times wavelength. And so we can get that wave's velocity. Last but not least, we can also get the period, because we know the period is the inverse of the frequency. We said that the frequency of this was the angular frequency divided by 2 pi. So therefore, the period is just 2 pi over the angular frequency. So just by knowing the mathematical form of the wave, just by knowing the mathematical form of the wave, we can literally figure out all the other pieces as to what properties this wave has. By the same token, if we're given a picture of a wave, we can basically do the exact same thing. Let's make sure that we're all on the same page with that. Let's say that we had a wave which looked something like this on a picture. And let's say that all those crests and troughs were the same distance, etc. Okay? And let's say that we called this, I don't know, 7 on whatever unit set is in the y direction. Let's say that this was 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. Okay? And let's say that the x-axis was a time axis. Okay? And let's also say that we knew this was a sound wave. So we know its velocity is 343 meters per second. From this picture, find everything else out you can about the wave, and then try to write it in mathematical form. Let's do it. Right? What's its amplitude? Its amplitude is how high it goes. The amplitude, right, is meant to be 7. Okay. From the x-axis, right, if the time axis there, right, goes up to 4 seconds, right, we can see then exactly what the frequency or period of this wave is, right? Because it takes 4 seconds to complete one, and I'll highlight it in red. Do we all agree there's one wavelength or one repetition of the wave? So the period is 4 seconds. Ladies and gentlemen, if we know the period, we know the frequency is 1 over the period. If we know the frequency, we know the angular frequency is 2 pi times the period. If we know the frequency, 1 over 4, and we know the velocity, we also know that velocity is equal to lambda times frequency, so we can solve this for the wavelength. If we know the wavelength, we know k is 2 pi over the wavelength. I'm not going to bother plugging that in, but you see what I'm getting at here, yes? So now, Just by staring at the picture, we know the amplitude, we know the period, we know the frequency, we know omega, we know the velocity, we know the wavelength, we know the wave number. So can we write it in standard form? Yes. 7. This is a sine function because it begins from 0. K was 2 pi over the wavelength, which I guess I will write it in now. X minus omega, which we said was pi over 2. And there is our mathematical form of the wave. Not so bad, right? That is our laundry list of properties of the wave. And from that laundry list of properties, that is how we can get the mathematical form. And then I walked us through how we can take the mathematical form and peel different pieces out of that. And then if we peel different pieces out from that, then we can also do the same thing from a graphical form. Okay, ladies and gentlemen, that's all that I have to say about the basic properties of waves. I was gonna stuff in some optics here, okay, but I think I'm gonna save that for the next video. That way it's not making this video too long in length. So now let's make sure that we get this video in our brains as best as possible. And in the next one, like I said, we'll jump from talking about just the properties of waves themselves and talking about electromagnetic waves and how they travel and how that leads us to the basic conclusion of things like optics. Until then, ladies and gentlemen, I hope you have a fantastic day. And as always, questions, comments, complaints, and concerns, please don't hesitate to reach out.